Hi, I welcome you all for my first video lecture on course Computer Organization and Architecture. I am Professor CMT Karthikeyan, working for Computer Science and Engineering Department, Government College of Engineering, Burger. This is the agenda for our today's discussion. We are going to discuss a topic, booth multiplication algorithm under the unit computer arithmetic. First, we are going to see the requirements of booth multiplication algorithm, and then we are going to discuss the algorithm followed by worked out example, and finally we are going to verify the results against the algorithm. Yeah, now we should know what do you mean by booth multiplication algorithm. Why do we need to know this concept? Booth multiplication algorithm, it is an algorithm for multiplying two signed numbers using 2's complement method. And moreover, this course computer organization and architecture focuses on how the operations are being performed internally by the computer. This algorithm can be taken as one example how two signed numbers are being multiplied internally by the computers. This algorithm involves four registers, namely VAC, BR, QR, and SC. We'll see the purpose of each and every register one by one. The first one is called as an AC register, otherwise it is called as an accumulator register. It is used to perform arithmetic and logical operations involved in the algorithm, and the result will be stored back to an accumulator. And the second register called BR register is used to hold the multiplicand value. What do you mean by multiplicand value? If you are performing a multiplication operation A into B, the first operand A is called as a multiplicand and second operand B is called as multiplier. Here the multiplicand is stored in BR. QR is used to store the second operand of the multiplication operation called as multiplier. And we should further know little about QR register. QR, the rightmost bit of QR register is QN, and the bit coming out of QR register will be captured by QN plus 1 while we are performing an arithmetic shift right operation. Right? Now we'll see what do you mean by an arithmetic shift right operation later in the slide. Finally, the most important register called as a sequence counter, or simply it is abbreviated as an SC. It is going to hold a non-zero value. This only decides how many times this algorithmic process should be repeated. Once the sequence counter comes to 0, there the algorithmic process comes to an end. At that point, the registers will be having the end result. So as I already told you about that, we have to discuss about, or we have to know about arithmetic shift right operation before proceeding to an algorithm. So this is the scenario of an arithmetic shift right operation, right? I have told you about signed numbers. What do you mean by signed numbers? The numbers with the sign. So we know that for computers, we need to represent everything in terms of zeros and ones. In the same way, the signs also have to be represented by zeros and ones. 0 is used to represent a positive sign and 1 is used to represent a negative sign. As far as this example concerned, we'll come to know that the number is negative by looking into the sign bit. Sign bit is nothing but the most significant bit of a given binary number. Now we'll see how this arithmetic shift operation works. The sign bit will be retained in the same position as well as it is copied on to the next bit position, and the bits in the respective positions will be moved on to the next positions in the cascade. Right? The rightmost bit called as Q1 will be coming out while performing a shift right operation, and it is getting placed in 1 bit register called as an Qn plus 1. So now we'll see what is happening after arithmetic shift right operation. You can see here this 1 is a sign bit that is retained here, and it is getting copied onto the next bit position. That is why 1 comes in the second position also. This 0 is moving on to the third position, that is 0. This one is moving on to the fourth position, that is 1 is coming here. Similarly it goes on, and the rightmost bit position called as 0 will be moving on to a 1 bit register called as an Qn plus 1. Yeah. Now we are going to discuss the algorithmic flow of a Booth multiplication algorithm. Multiplicand is placed in a register called as BR, and the multiplier is in QR. These are all the initial setup for an algorithm before the actual process begins. AC is initialized with 0, Qn plus 1 is 0, and SC is equal to n. N is nothing but the number of bits stored in multiplier. This whole algorithm works based on the bits of Qn and Qn plus 1. If Qn plus 1 is equal to 0, 1, the content of BR is added with accumulator and the result stored in accumulator, followed by we need to perform an arithmetic shift right operation on accumulator and QR register and decrement the sequence counter by 1. If Qn plus 1 equal to 1, 0, we need to subtract BR, and then we need to store the result back to the accumulator, followed by we need to perform an arithmetic shift right operations on accumulator and QR. And decrement the sequence count. If Qn and Qn plus 1 is either 0, 0 or 1, 1, we need to perform only an arithmetic shift operations on AC and QR, followed by decrementing the sequence counter. So overall, for every time the sequence counter is getting decremented, the algorithmic process checks whether sequence counter reaches 0 or not. If sequence counter reaches 0, we need to we have come to the end of the algorithm. The result will be stored in AC and QR. If not equal to 0, the process is repeated. Right? So this is the flow of an Booth multiplication algorithm. Now we'll see an worked out example for that. So now we are going to work for minus 3 into 4. So literally, as far as a layman, we can say that it is minus 12. But we need to make the computers understand this minus 3 and 4 in its own way, and how this computer is going to perform this minus 3 into 4 now through this Booth multiplication algorithm. Okay, as I already told you that the most significant bit represents the sign bit. Okay, now we need to represent minus 3. For that we should first know how to represent plus 3. So first we have taken plus 3 equal to 0. 0 is used to represent the positive sign, and remaining bits form the number. Then we have all, once again I am reminding you that this algorithm uses 2's complement method. So if you find the 2's complement method including the sign bit, we will get the corresponding negative equivalent of a number. So now we are going to find the 2's complement of this value 0, 0, 1, 1. We are getting as 1, 1, 0, 1. Now this is nothing but minus 3. We will also confirm that by looking into the sign bit. 1 is there, so it is a negative equivalent. So in the negative equivalent we cannot get the exact equivalent of a binary number. We can get the familiar form only in the positive equivalent. If the number is in not in familiar form, we'll come to know that it is in 2's complement form, right? Okay. Next is multiplier. Multiplier is 4 plus 4. So we are representing as 0 is used to represent the positive sign plus. Remaining bits called as 100 forms the number called as 4. BR is placed as BR. What is the BR value? BR is going to hold multiplicand, that is nothing but minus 3, 1, 1, 0, 1, and BR dash plus 1 is nothing but the 2's complement of this minus 3, which is we are going to get the positive sign. That is, while you are performing a 2's complement of positive number, you will get a negative equivalent, and vice versa. If you find the 2's complement of negative number, we will get a positive equivalent. Now we will get into the algorithm. We know that AC is initialized with 0 0, so we have taken 4 bits, so it is 0 is represented with 4 bits. QR is to hold a multiplier. Here the multiplier is 0 1 0 0, and Qn plus 1 is initialized with 0, and sequence counter we know that it is 4. Number of bits is in multiplier. Now the algorithm starts. Qn plus 1 0 0 0 0. Here rightmost bit of QR is 0. Qn plus 1 is also 0. So 0 0 0 0 means we just perform an arithmetic shift operation on AC and QR. So we'll be getting this. That is the rightmost bit will be moving on to Qn plus 1 and decrementing the sequence counter by 3. So decrementing the sequence counter by 1, by which we are getting 3. Once again we are looking, so the sequence counter is not equal to 0. The process repeats. Once again we are looking into Qn and Qn plus 1. Once again it is 0 0. We are going to perform an arithmetic shift right on AC and QR. Now we have got this value, and the rightmost bit is 0, and we are decrementing the sequence counter by 1. Now it is 2. So now the Qn plus 1 value is 1 0. 1 0 means we are going to subtract BR, right? Subtract BR is nothing but BR bar plus 1. So we are going to add the accumulator with BR bar plus 1. So AC is already 0 0 0. 0 0 0 is added with 0 0 1 1 means we will be getting 0 0 1 1. Right? This QR value will be retained as it is. Then we need to perform an arithmetic shift right. After adding this, adding BR bar plus 1, we need to perform an arithmetic shift right operation. So here we are going to get the rightmost significant bit as 1, and then decrement the sequence counter by 1. We will be getting 1 now. Now the value of Qn plus 1 is 0 1. 0 1. 0 1 means what we need to do? We need to perform, or we need to add BR with AC and store the result back to an AC. Okay, here 0 0 0 1 is an AC value because the recent value is 0 0 0 0 1, and it should be added with BR 1 1 0 1. 1 1 0 1 plus 0 0 1 is nothing but 1 1 1 0, and QR value will be retained as it is. Qn plus 1 value will be retained as it is. After performing addition, we need to perform an arithmetic shift right on AC and QR. We are performing that, and we are decrementing the counter. It reaches 0. As the algorithm tells, the final value will be in AC and QR. So by looking into the result, we'll come to know that the result is negative. Look into the most significant bit. Here it is 1. So result is negative. As I already discussed that if the result is negative, the result won't be in the familiar form. So what we should do? We'll see it in the next slide. Here result is in AC and QR. If the result is negative, result will be in respective complement form. I have already told that it is in 2's complement form. To verify the answer in our familiar form, we have to recomplement the result. Here the case is we need to perform the 2's complement on the result. Here our actual result, that is 4 1s 0 1 0 0 is our result. We need to find the 2's complement. What do you mean by 2's complement? 1's complement plus 1. 1's complement of this number is 4 zeros 1 0 1 1. Then plus 1 will give this result, that is 4 zeros followed by 1 1 0 0, which is nothing but an 12. 1 1 0 0 is nothing but an binary equivalent of 12, and we need to put the negative sign. Okay, after recomplementing it, we need to put the negative sign for a number. So what we'll get if you put a negative sign for minus 12, if you put negative sign for 12, we'll get minus 12. So that is our result, right? So we have verified the algorithm successfully. Thank you for your patient listening.